Western Germany, February 11, 1945, 1400 hours, and Oberleutnant Heinrich Roth of Jagdgeschwader 26 pushed his control stick hard right at 400 miles per hour, feeling the muscles in his arm burn as the stick barely moved a centimeter. His Focke-Wulf Fw 190 refusing to respond while the Hawker Tempest behind him rolled effortlessly into firing position, its four 20mm cannons already tracking toward his cockpit. The control stick felt welded in place, requiring over 60 pounds of force just to achieve minimal deflection, and Roth knew with crystalline certainty that he was about to die because his aircraft's ailerons had become essentially frozen at this speed, while the British fighter behind him seemed to maneuver as easily as if flying at half the velocity, something that should have been physically impossible according to everything the Luftwaffe's engineers understood about high-speed flight dynamics. 3 seconds later, 20mm shells shattered Roth's canopy, and as his Fw-190 spiraled toward the German countryside, he became another casualty of a technological revolution that the Wehrmacht's brightest engineers hadn't even known existed, a simple device called a spring tab that transformed the Hawker Tempest into something that defied every assumption German pilots held about combat at 400 miles per hour. The spring tab aileron system was destroying Germany's finest fighter pilots at an alarming rate by February 1945, with 47 Luftwaffe pilots killed in January alone during encounters with Tempests, most of them discovering too late that their aircraft became nearly uncontrollable at speeds where the British fighter maintained perfect maneuverability, a disparity that transformed high-speed combat from a test of skill into an execution. The story of Germany's fatal disadvantage in high-speed control systems began much earlier, in the summer of 1944, when the first reports reached Luftwaffe headquarters about a new British fighter that seemed to violate the laws of physics, maintaining full aileron control at speeds where both the Messerschmitt Bf 109 and Focke-Wulf Fw 190 experienced control forces so severe that pilots physically couldn't move their sticks enough to maneuver effectively. Major Wilhelm Steinmann, commanding 2 Gruppe of Jagdgeschwader 26, had dismissed these early reports as exaggeration or pilot error, insisting that no aircraft could maintain light control forces at 400 miles per hour because the aerodynamic pressures at such speeds made large control surface deflections physically impossible without hydraulic assistance, which added weight and complexity that no single engine fighter could afford. Steinmann's certainty came from extensive experience with Germany's best fighters, knowing that the Fw-190, despite being one of the most advanced aircraft in the Luftwaffe's arsenal, required tremendous physical strength to maneuver at high speeds, with pilots needing to apply 45 to 60 pounds of lateral force on the stick to achieve even modest roll rates above 350 miles per hour. The Messerschmitt Bf 109 faced even worse problems, its narrow cockpit physically preventing pilots from applying more than 45 pounds of side force to the stick, making full aileron deflection impossible at combat speeds, a limitation that had killed hundreds of German pilots who found themselves unable to maneuver when diving to escape Allied fighters, their controls becoming progressively heavier until they might as well have been carved from stone. The technical limitation seemed insurmountable because it stemmed from basic physics. As airspeed increased, the aerodynamic forces acting on control surfaces grew exponentially, requiring ever greater pilot strength to overcome, creating a deadly paradox where the faster an aircraft flew, the less maneuverable it became until at maximum speeds, fighters became essentially straight-line missiles, unable to turn or roll effectively. German engineers had tried various solutions, including the installation of Flettner tabs on some Bf 109G variants, small auxiliary surfaces that helped reduce control forces, but these provided only marginal improvement and were fitted to relatively few aircraft, leaving most Luftwaffe pilots to rely on raw physical strength and careful speed management to maintain any control authority at high velocities. The Reich's aeronautical engineers working at facilities in Augsburg, Dessau, and Rechlin had concluded that significantly reducing control forces at high speed without hydraulic boost was technically impossible, accepting heavy controls as an unavoidable characteristic of high-performance fighters, a limitation they believed affected all nations equally. This assumption proved catastrophically wrong when the Hawker Tempest entered combat in April 1944, bringing with it a technology that German engineers hadn't even considered, a spring-tab aileron system that automatically reduced control forces as speed increased, allowing British pilots to maintain fighter trainer-like control sensitivity at speeds where German pilots could barely move their sticks. The spring tab mechanism was deceptively simple, consisting of a small auxiliary control surface mounted on the trailing edge of each aileron, connected to the main control system through a calibrated spring that compressed under aerodynamic loads. causing the tab to deflect in the opposite direction to the aileron movement, generating an aerodynamic force that helped move the main control surface. As airspeed increased and aerodynamic loads grew heavier, the spring compressed more, causing greater tab deflection and providing increased assistance, automatically compensating for the speed-induced control heaviness that plagued conventional aileron systems, maintaining nearly constant stick forces across the entire speed range. British test pilot Eric Brown, who would later evaluate captured German aircraft, had noted during his first Tempest flights that the spring tabs made the aircraft feel almost unnaturally responsive at high speeds, maintaining roll rates that would have required superhuman strength in conventional fighters, describing the sensation as like power steering before power steering existed, allowing precise, effortless control inputs at velocities where other fighters became barely controllable. The system had been developed through extensive wind tunnel testing at the Royal Aircraft Establishment at Farnborough, with Hawker's engineers at their Langley facility spending months perfecting the spring rates and tab geometry to achieve optimal force reduction without introducing flutter or other aeroelastic problems that could destroy the aircraft in high-speed flight. German pilots first encountered this technological advantage during the Normandy campaign, when Tempests began appearing over the battlefield in increasing numbers, and combat reports started describing impossible maneuvers, with British fighters maintaining aggressive rolls and turns at dive speeds where German aircraft became virtually immobilized by control forces. Hauptmann Joseph Priller, one of the Luftwaffe's most experienced aces with over 100 victories, encountered a Tempest during a high-speed engagement over Belgium in September 1944, later describing how his FW-190 became like flying in concrete at 400 miles per hour, while the British fighter danced around like it was at stall speed, executing a barrel roll that would have been physically impossible for him to match. The combat reports accumulated through the autumn of 1944, painting a disturbing picture of technological inferiority that challenged everything the Luftwaffe believed about their aircraft, with pilot after pilot describing the same phenomenon of being outmaneuvered at speeds where they could barely maintain straight flight. The problem was particularly acute for Bf-109 pilots, whose narrow cockpits physically constrained their ability to apply lateral stick forces, creating situations where they would enter high-speed dives to escape combat, only to find themselves trapped in essentially straight-line flight paths while Tempests followed them down, maintaining full maneuverability throughout the descent. By November 1944, the situation had become critical enough that General der Jagdflieger Adolf Galland ordered a technical investigation into the Tempest's mysterious capabilities, assigning a team of engineers from the Messerschmitt and Focke-Wulf companies to analyze combat footage and crashed aircraft remains, searching for the secret that allowed British pilots to maintain control at speeds where German fighters became flying bricks. The investigation initially focused on the wrong areas, with engineers assuming the British had developed some form of hydraulic boost system or revolutionary aerodynamic design, not recognizing that the answer lay in a relatively simple mechanical device that had been visible in crashed aircraft but dismissed as merely another type of trim tab. The revelation finally came in December 1944, when Luftwaffe technical intelligence officers at Rechlin examined a relatively intact Tempest that had been forced down near Rain Airfield, discovering for the first time the true nature of the spring tab system and realizing with growing horror that this simple mechanism solved the control problem that had been killing German pilots for months. The examining engineers, led by Dr. Friedrich Zimmermann from the Deutsche Versuchsanstalt für Luftfahrt, initially refused to believe that such a basic mechanical system could provide such dramatic improvements, conducting hasty calculations that confirmed the spring tab's effectiveness at reducing control forces by up to 70% at maximum speeds. Zimmermann's report to the Air Ministry described the discovery in stark terms, noting that the enemy has equipped their latest fighter with a control system that provides advantages we had not considered possible, allowing their pilots to maintain full combat maneuverability at speeds where our aircraft become marginally controllable, adding that retrofitting similar systems to existing German fighters would require extensive redesign and flight testing that could take months or years. The report triggered a crisis meeting at Luftwaffe headquarters, where Galland confronted Hermann Göring with the reality that British fighters possessed a decisive technological advantage that couldn't be quickly countered, contributing to the growing tension between the Luftwaffe leadership and the Nazi hierarchy about the conduct of the air war. The Japanese, Germany's Axis partners, faced similar shock when encountering American fighters equipped with advanced control systems, with pilots of the Imperial Japanese Army Air Force discovering that their manually controlled fighters became virtually unflyable at speeds where American P-51 Mustangs and P-47 Thunderbolts maintained crisp control response, though they never fully understood the technical reasons for this disparity. Japanese ace Makoto Ogawa, who shot down 7 B-29 bombers, noted in his post-war memoirs that engaging American fighters in high-speed combat was like fighting with one hand tied behind your back, as the Zero and other Japanese fighters experienced control forces that made aggressive maneuvering physically impossible above 300 miles per hour. The Italians, flying their Macchi C-202 Folgore and C-205 Veltro fighters, had attempted to address control heaviness through various means, including interconnected aileron flap systems that provided some assistance, but nothing approaching the effectiveness of the British spring tab system, leaving them vulnerable to the same high-speed control limitations that plagued their German allies. Squadron leader Franco Lucchini, one of Italy's top aces, had complained repeatedly about the Macchi fighters becoming wooden at high speeds, requiring tremendous physical effort to execute even basic maneuvers when pursuing or escaping from Allied fighters in high-speed engagements. The production of Tempests with spring tab ailerons had begun at Hawker's Langley facility in 1943, with the system being progressively refined through extensive flight testing that revealed optimal spring rates and tab dimensions for maximum effectiveness without introducing structural risks. The initial production batch of 100 Tempest V-Series I aircraft had featured the spring tab system, though some were temporarily withdrawn from combat in late 1944, when it was discovered that the dramatically increased maneuverability could overstress the airframe if pilots applied maximum control inputs at limiting speeds, requiring minor structural reinforcements and pilot training on the new handling characteristics. Sidney Cam, Hawker's chief designer, had recognized early in the Tempest development that high-speed control forces would be a critical limitation, drawing on experience from the earlier Typhoon, which had suffered from extremely heavy controls that exhausted pilots during extended combat engagements. The spring tab solution had emerged from collaboration with the Royal Aircraft Establishment, where aerodynamicists had been exploring various methods of control force reduction, eventually settling on the spring tab as offering the best combination of effectiveness, simplicity, and reliability without the weight and complexity penalties of hydraulic systems. The manufacturing process for the spring tab-equipped ailerons required precise calibration of the spring mechanisms, with each aircraft being individually tested to ensure proper tab response across the speed range, a level of quality control that would have been difficult for German manufacturers to achieve given the deteriorating conditions in Reich factories by 1944. Workers at Hawker's Langley plant, many of them women who had replaced men called to military service, assembled the spring tab mechanisms with tolerances measured in thousandths of an inch, understanding that their precision work would directly translate to pilot survival in combat at 400 miles per hour. The combat effectiveness of the spring tab system became undeniable during the period from December 1944 through February 1945, when Tempest-equipped squadrons claimed 239 German aircraft destroyed for the loss of only 20 Tempests, achieving a 7-to-1 kill ratio that reflected not just pilot skill but the decisive advantage of maintaining control at speeds where enemy fighters became practically helpless. Squadron leader David Fairbanks, the highest-scoring Tempest ace, described engagements where German fighters would attempt to escape in high-speed dives, only to find themselves trapped in straight-line flight while he could still perform aggressive maneuvers to maintain optimal firing position, turning what should have been successful escape attempts into turkey shoots. The psychological impact on Luftwaffe pilots was devastating, as they realized their aircraft suffered from a fundamental disadvantage that no amount of skill or courage could overcome, creating a crisis of confidence that spread through fighter units facing Tempests on a daily basis. Oberfeldwebel Kurt Bulligan of Jagdgeschwader Fw, a veteran with over 100 combat missions, wrote in a letter to his wife in January 1945 that we are fighting with yesterday's weapons against tomorrow's technology, describing the helpless feeling of watching Tempests maneuver freely at speeds where his Fw-190 became heavy as a loaded bomber. German attempts to quickly implement similar technology faced insurmountable obstacles, as the Reich's aviation industry struggled with material shortages, factory dispersal due to bombing, and the loss of experienced engineers to military service or Allied captivity, making the extensive redesign and testing required for spring tab implementation practically impossible. Some Fw-190D-13 variants received hydraulic aileron boost as an emergency measure, but only a handful were produced before the war ended, and the system added weight and complexity that degraded performance in other flight regimes, representing a poor substitute for the elegant simplicity of the spring tab solution. The Luftwaffe's fighter force, already suffering from fuel shortages, inexperienced pilots, and numerical inferiority, found the technological disadvantage in control systems to be one more factor accelerating their defeat, as pilots increasingly avoided high-speed combat situations where they knew they would be at a fatal disadvantage. Operations like Bodenplatte on January 1, 1945, where the Luftwaffe launched a massive surprise attack on Allied airfields, were partially motivated by the need to destroy Allied fighters on the ground because engaging them in aerial combat, particularly at high speeds, had become increasingly suicidal for German pilots facing aircraft like the Tempest with superior control characteristics. The spring-tab advantage extended beyond pure combat effectiveness, as Tempest pilots could maintain aggressive pursuit tactics that would have exhausted pilots flying conventional fighters, the reduced control forces allowing them to fly longer missions with less physical fatigue, maintaining peak performance throughout extended engagements. Flight Lieutenant Pierre Klosterman of 274 Squadron noted that after transitioning from Spitfires to Tempests, he found he could fly twice as long without experiencing the arm and shoulder fatigue that had limited his effectiveness in prolonged dogfights, the spring tabs making control inputs feel like moving through air instead of molasses at combat speeds. Technical analysis conducted after the war at Wright Field in the United States, where captured German fighters were extensively tested, confirmed the severe control force problems that had plagued the Luftwaffe, with American test pilots expressing amazement that German pilots had achieved any success at all given the physical limitations of their aircraft at high speeds. The evaluation reports noted that the Fw-190, despite excellent low and medium speed handling, became marginally controllable above 400 miles per hour, requiring control forces that would challenge a weightlifter, while the Bf-109G was even worse, with its narrow cockpit making it physically impossible for most pilots to apply sufficient lateral force for full aileron deflection. Captain Eric Brown of the Royal Navy, who tested both German and British fighters extensively, provided perhaps the most damning assessment, noting that the Fw-190's lack of spring tabs or similar control aids meant that, at maximum speed, the aircraft might as well not have ailerons at all, while the Tempest maintained fighter-trainer responsiveness throughout its speed range, a disparity he described as the difference between having a weapon and having a club. His evaluation of the Bf-109G was even more critical, observing that the combination of narrow cockpit and heavy controls created a death trap in high-speed combat, where pilots simply couldn't physically generate enough force to maneuver effectively, regardless of their skill or determination. The Italian evaluation of captured Allied aircraft after Italy's surrender revealed similar amazement at the advanced control systems, with Regia Aeronautica test pilots reporting that flying a Tempest after their Macchi fighters was like switching from a truck to a race car, particularly noting the ease of control at speeds where Italian fighters required maximum physical effort. Major Adriano Visconti, one of Italy's most successful fighter pilots, flew a captured Tempest in early 1945 and reported that the spring tab system would have changed everything if Italian fighters had possessed similar technology, potentially altering the balance of air combat over the Mediterranean. The Japanese, despite their reputation for innovative aircraft design, never developed effective solutions to high-speed control problems, with their emphasis on lightweight construction and maneuverability at low speeds leaving their fighters essentially helpless in high-speed engagements against American aircraft with advanced control systems. Post-war interrogations of Japanese pilots revealed that many never understood why American fighters could outmaneuver them at high speeds, attributing it to superior pilot training or mysterious technology rather than recognizing the fundamental advantage provided by systems like spring tabs that maintained control effectiveness across the entire speed envelope. Soviet engineers, who examined captured German aircraft and received some British technical information through Lend-Lease arrangements, quickly recognized the importance of control force reduction, implementing various solutions in their post-war designs, though they initially struggled to achieve the same elegance and effectiveness as the British spring tab system. The Yakovlev Design Bureau particularly studied the problem, with Alexander Yakovlev himself noting that the spring tab represented a simple solution to a complex problem that we had been approaching from entirely wrong angles, leading to improved control systems in later Soviet fighters. The French aviation industry, rebuilding after the war with access to both German and Allied technology, conducted extensive studies on control systems, with engineers at SNECMA concluding that the spring tab represented one of the war's most significant but underappreciated technical innovations, providing advantages that decided countless air battles without most participants understanding why. Marcel Dassault, whose company would become one of Europe's leading fighter manufacturers, insisted that all future designs incorporate advanced control aids, having seen the fatal consequences of the control force limitations that had crippled Axis fighters. The production statistics tell their own grim story, with Hawker manufacturing 1,702 Tempests by war's end, most equipped with spring-tab ailerons, while German attempts to retrofit similar systems to existing fighters produced only a handful of modified aircraft before the Reich's collapse. The Langley factory alone was producing Tempests at a rate of 15 per week by early 1945, each one representing another Allied fighter that could dominate high-speed combat, while German factories struggled to maintain any production at all under constant bombing and resource shortages. The human cost of this technological disparity was staggering, with German fighter losses reaching unsustainable levels by early 1945, forcing the Luftwaffe to increasingly avoid combat except under the most favorable conditions, effectively ceding air superiority to the Allies. In January 1945 alone, when 47 German pilots died fighting Tempests, the Luftwaffe lost the equivalent of an entire fighter group's experienced pilots, losses that couldn't be replaced given the collapse of Germany's training programs and the poor quality of replacement pilots who had minimal flight hours before entering combat. The psychological warfare aspect of the spring-tab advantage shouldn't be underestimated, as word spread through Luftwaffe units about the Tempest's seemingly supernatural maneuverability, creating fear and defeatism that affected combat performance even before engagements began. Pilots who had once been aggressive and confident became hesitant and defensive, knowing that entering a high-speed engagement with a Tempest was virtually suicidal, leading to a cascade of tactical disadvantages as German fighters increasingly fought from positions of weakness. Wing Commander Roland Beaumont, who led the first Tempest wing into combat, later reflected that the spring-tab system had provided an ace-up-our-sleeve that the Germans never saw coming, transforming what could have been a good fighter into a dominant one through a relatively simple mechanical innovation. He noted that many of his pilots never fully appreciated the advantage they possessed, assuming their success came from superior training or tactics rather than recognizing that they were flying aircraft with fundamentally superior control characteristics that made them nearly unbeatable in high-speed combat. The maintenance and reliability advantages of the spring-tab system compared to hydraulic alternatives also proved significant, as the mechanical system required minimal maintenance and rarely failed, while hydraulic systems added complexity, weight, and potential failure points that could leave pilots without control assistance at critical moments. Ground crews at forward airfields could maintain and adjust spring-tab systems with basic tools, while hydraulic systems required specialized equipment and expertise that would have been increasingly difficult for the Luftwaffe to provide as their logistics network collapsed. The aerodynamic efficiency of the spring-tab solution also deserves recognition, as the small tabs added minimal drag while providing maximum benefit, unlike larger balance tabs or other mechanical aids that could significantly impact performance, a crucial consideration in fighter design where every mile per hour of speed could mean survival. Wind tunnel testing at Farnborough had optimized the tab size and placement to provide maximum control force reduction with minimum drag penalty, achieving a level of refinement that German engineers, working under wartime pressure and resource constraints, couldn't hope to match. The training implications of the spring-tab system extended beyond combat advantages, as Tempest pilots required less physical conditioning to fly effectively, allowing older or smaller pilots to remain combat effective in situations where flying conventional fighters would have been physically exhausting or impossible. This expanded the pool of potential pilots and reduced training washout rates, advantages that became increasingly important as the war dragged on and experienced pilots became scarce, while the Luftwaffe struggled with pilots who simply lacked the physical strength to effectively control their aircraft at combat speeds. The spring-tab technology represented a perfect example of British pragmatic engineering, solving a critical problem with elegant simplicity rather than complex over-engineering, an approach that contrasted sharply with German tendencies towards sophisticated but complicated solutions that often proved unreliable or difficult to manufacture. While German engineers pursued hydraulic systems, variable geometry wings, and other complex solutions to the control problem, British engineers achieved superior results with springs and small metal tabs, a disparity that reflected fundamental differences in engineering philosophy that influenced the war's outcome. Post-war analysis by the United States Strategic Bombing Survey concluded that technological advantages like the spring-tab system had cumulative effects far beyond their immediate combat impact, contributing to the collapse of German morale and the recognition that the Third Reich had fallen behind in critical technologies. The report noted that German pilots and engineers had assumed rough technological parity with the Allies, making discoveries like the spring-tab system particularly devastating to confidence, revealing that the supposed superiority of German engineering was increasingly illusory. The influence of the spring-tab innovation extended far beyond World War II, with variations of the technology appearing in civilian and military aircraft for decades afterward, testament to the fundamental soundness of the concept that Hawker engineers had pioneered under wartime pressure. Modern fly-by-wire systems that provide artificial feel and automatic control force variation can trace their conceptual lineage back to the simple spring tabs that gave Tempest pilots such a decisive advantage, showing how wartime innovation could have lasting impacts on aviation technology. The story of the spring tab also illustrates the danger of technological assumptions and the importance of continuous innovation, as German engineers' certainty that high-speed control problems were unsolvable without complex hydraulic systems blinded them to simpler solutions that their enemies had already implemented. This technological blind spot cost hundreds of German pilots their lives and contributed to the Luftwaffe's inability to contest Allied air superiority in the war's final months, showing how a single overlooked innovation could have strategic consequences. The personal accounts of German pilots who survived encounters with Tempests provide visceral testimony to the terror of finding oneself helpless at high speed, unable to maneuver while an enemy fighter maintained complete control, turning what should have been the advantage of a high-speed dive into a death trap. Unteroffizier Wilhelm Hoffmann, who survived being shot down by a Tempest in February 1945, described the experience as like being paralyzed while someone beats you, his Bf-109G becoming completely unresponsive at 400 miles per hour, while the Tempest behind him moved like it was dancing. The industrial archaeology of the Hawker Langley factory, though largely destroyed by post-war development, revealed evidence of the precision manufacturing required for spring tab production, with specialized jigs and fixtures designed to ensure consistent spring rates and tab alignment across hundreds of aircraft. Workers' memoirs describe the emphasis placed on quality control for these seemingly simple components, with management stressing that a tenth of an inch could mean a pilot's life. Recognition that the spring tabs weren't just parts but life-saving technology that could determine combat outcomes. The classified nature of the spring tab technology during the war meant that even many Allied pilots didn't fully understand the advantage they possessed, with squadron intelligence officers instructed to describe the system in vague terms if captured, protecting the secret that was providing such decisive advantages. German intelligence services, despite extensive efforts to gather technical information on Allied aircraft, never fully grasped the significance of the spring tab system until examining crashed aircraft, by which time it was too late to develop effective countermeasures. The economic impact of the control system disparity extended beyond direct combat losses, as the Luftwaffe was forced to allocate precious resources to developing emergency solutions like hydraulic boost systems that might have been better spent on producing more aircraft or training more pilots. The man-hours spent investigating and attempting to counter the spring tab advantage represented a hidden cost of technological inferiority, draining German resources at a time when every asset was critical to the Reich's survival. The international recognition of the spring tab's importance came slowly, with many post-war histories focusing on more dramatic innovations like jet engines or radar, overlooking the simple mechanical device that had provided such decisive advantages in conventional fighter combat. Only in recent decades, as aviation historians have conducted more detailed technical analyses of World War II aircraft, has the full significance of the spring tab system been recognized, revealing how a seemingly minor innovation could have major strategic impacts. The testimony of Luftwaffe ground crews provides another perspective on the control system crisis, with mechanics describing pilots returning from missions physically exhausted from fighting heavy controls, sometimes unable to fly again for days due to muscle strain, while Tempest pilots could fly multiple missions per day without similar fatigue. Chief Mechanic Otto Bergmann of Jagdgeschwader 26 noted that pilots increasingly requested any modifications that might lighten control forces, leading to dangerous field modifications like removing armor plating to reduce weight, desperate measures that reflected the severity of the disadvantage. The spring tab story also highlights the importance of incremental innovation and continuous improvement, as the system fitted to Tempests represented years of development and refinement dating back to interwar research on control systems, showing how peacetime investment in seemingly mundane technology could provide decisive wartime advantages. The Royal Aircraft Establishment's systematic approach to solving the control force problem, involving extensive wind tunnel testing and theoretical analysis, contrasted with the more ad hoc German approach that failed to identify viable solutions until too late. The cultural factors that contributed to German engineers overlooking spring tab technology deserve consideration, including a tendency toward complex, sophisticated solutions that demonstrated technical prowess rather than simple, practical fixes that merely solve problems effectively. The German engineering establishment's focus on revolutionary advances like jet propulsion and rocket technology, while producing spectacular innovations, may have caused them to overlook evolutionary improvements like spring tabs that could have immediate practical benefits. The adaptation of spring tab technology to different aircraft types after the war demonstrated its versatility and fundamental soundness, with variations appearing on everything from civilian airliners to military transports, proving that the concept Hawker pioneered for the Tempest had applications far beyond fighter aircraft. The Douglas DC-6 and other post-war airliners incorporated spring tab systems directly inspired by wartime fighters, showing how military innovation could benefit civilian aviation, though the origins in the desperate air battles of 1944-45 were rarely acknowledged. The final months of the war saw increasingly desperate German attempts to counter the Tempest threat, including orders to avoid combat unless possessing numerical superiority and altitude advantage, tactical restrictions that further reduced the Luftwaffe's effectiveness and contributed to Allied air dominance. The infamous Ramjager units, trained to ram Allied bombers in suicide attacks, were partially motivated by the impossibility of conducting conventional interceptions when fighters like the Tempest could dominate any aerial engagement through superior control at high speeds. The human drama of young German pilots, many with less than 50 hours of flight time, being sent into combat against Tempests with their spring tab advantages represents one of the war's many tragedies, as these inexperienced aviators faced not just better trained enemies but aircraft with fundamental technological advantages they couldn't overcome. Training schools attempted to prepare new pilots for the control force problems they would face, but no amount of instruction could overcome the physical impossibility of maneuvering effectively at speeds where Tempests retained full control authority. The preservation of surviving documentation about spring tab development and implementation provides valuable insights into wartime innovation processes, showing how British engineers methodically solved technical problems while maintaining production schedules and meeting urgent military requirements. The correspondence between Hawker's design office and RAF operational squadrons reveals continuous refinement based on combat experience, an iterative process that German manufacturers, isolated from frontline units by deteriorating communications and command structure, couldn't match. The role of test pilots in developing and validating the spring tab system deserves recognition, as men like Bill Humble and Philip Lucas risked their lives exploring the edges of the flight envelope to determine optimal spring rates and tab configurations, their methodical test flying providing data that would save countless combat pilots. Their reports, preserved in archives, reveal the systematic approach to solving control problems, with dozens of configurations tested before arriving at the final design that gave Tempests such decisive advantages in combat. The international proliferation of spring tab technology after the war, as former enemies became allies and technical information was shared, demonstrated how military innovation could transcend national boundaries and benefit global aviation development. German engineers who had struggled to understand spring tabs during the war later contributed to refining and improving the technology for civilian applications, showing how former adversaries could collaborate in peacetime to advance aviation technology. The statistical analysis of combat outcomes between Tempests and German fighters provides quantitative confirmation of the spring tab advantage, with engagement records showing that Tempests consistently achieved favorable exchange ratios even when outnumbered, particularly in high-speed engagements where the control system disparity was most pronounced. The mathematics of air combat, normally favoring numerical superiority, were overturned by technological advantage, as a single Tempest could effectively engage multiple German fighters that couldn't maneuver effectively at combat speeds. The metallurgical requirements for spring tab construction, particularly the springs themselves which needed to maintain consistent characteristics across wide temperature ranges and millions of compression cycles, represented another area where British industrial capability provided advantages that war-stressed German industry couldn't match. The special steel alloys required for reliable springs were increasingly difficult for Germany to produce as raw material sources were lost and factory facilities damaged, adding another layer to the technological disadvantage. The spring tab system's influence on pilot psychology and tactical doctrine extended beyond individual combat encounters, as the knowledge that Tempests possessed superior high-speed maneuverability forced German fighters to avoid entire categories of tactical situations, ceding initiative to Allied forces. The inability to conduct high-speed slashing attacks, once a favorite Luftwaffe tactic, removed a key tool from German pilots' arsenal, forcing them into disadvantageous turning fights where numerical inferiority and fuel limitations often proved decisive. The documentation of spring tab technology in technical manuals and training materials provides insights into how complex engineering concepts were communicated to pilots and ground crews who needed to understand the system's capabilities and limitations without extensive technical education. The simplified explanations and diagrams used to convey spring tab principles showed remarkable pedagogical sophistication, enabling effective use of the technology by personnel with varying technical backgrounds. The comparative analysis of different control force reduction methods attempted during the war reveals the spring tab's optimal balance of effectiveness, simplicity, reliability, and manufacturing feasibility, explaining why it succeeded where other approaches failed. German experiments with everything from aerodynamic balance tabs to servo tabs to hydraulic boost showed that while multiple solutions existed in theory, only the spring tab combined all necessary characteristics for successful wartime implementation. The evidence from crashed aircraft recovery and analysis shows that German technical intelligence services were aware of spring tabs by late 1944 but failed to grasp their full significance or develop effective countermeasures in time to affect the war's outcome. Intelligence reports describing the devices as modified trim tabs showed fundamental misunderstanding of their function and importance, a failure of technical analysis that cost the Luftwaffe dearly in the war's final months.